Okay, gang, I'm going to do number 31. We're going to look at concavity and inflection points. So I'm going to start with the derivative. I like to find the derivatives if they're not going to take me 20 minutes to do. It's usually the algebra that is 19 of the 20 minutes. Alright, so the first thing I'm going to do here to find the derivative is I'm going to bring the x value up to the numerator. You certainly can do the quotient rule as the inner part of the chain rule, but I think this is way easier. Alright, so overall this is chain rule. So first derivative, out e times in e. The outer layer of e is itself. You could just write it like the original if you prefer. That's the outer layer, that's the e. Derivative of the inner layer is going to be 3x to the negative 2. Alright, if you just want to see what that looks like in a more like nicer format, that would be 3 over e to the 3 over x times x squared. Alright, but we're not gonna I'm going to use this. I'm not going to use that. That's more, this is better format for me to do the second derivative. Because it's more of a, you want to do it more of a product rule versus a quotient and product. Alright, so here I go. Second derivative. So first times the derivative of the second piece. Derivative of the second piece is negative 6x to the negative 3. Okay, plus leave the second piece alone. Derivative of the first piece. Again, it's easier to do the derivative of the first piece in the altered format, which is this. Derivative of the outer layer times derivative of the inner layer. Okay, now you do the algebra. Because usually the students can get the calculus. It's really the algebra you have to work more on. It's the algebra and calculus is tricky. Not tricky, sophisticated. Sophisticated is a better word. I'm just rewriting things here. I'm not, sorry, I'm just changing the order here. Because I'm going to pull out the common factor. And you really want to squish or combine things before you do that. 3 times 3 is 9. You got negative 2 and negative 2, so it's negative 4. Hold on. You guys know it always takes me a second to catch if I faux pas, and the second has happened. That's like this. Yeah, just give me a second. If I write something wrong, I sometimes can catch it. If I don't, unfortunately, then I have to write the video, do the video over. Perks of movie making. Alright, did I do it here? I did. I could hear you guys saying, Professor Whelan, you missed one of the spots, and now I found it. Okay. I'm going to pull out what's common, so I don't know if you guys want to pull out the negative or not, it's up to you. So 3, and you can always fast forward if you have absolutely no interest in this part. Negative 4, it's just that a lot of you, it helps if you see a little more of the algebra, because you learn this in pre-calc, but it's a little fancier in the calculus. Okay, remember it's always the lowest exponent, so between the x's this is lower than this. Alright, so this is the common factor out here. Now I'm going to see what's left. I've got a negative 6 divided by 3 is 2. Remember, this is the bank. This is what you take out. So you started with negative 3. You're taking out negative 4. So it's actually a double negative, which makes a 1. So that means that what's left is actually an x. I know that looks weird, but that's accurate. Okay, now next one, 9 divided by 3 is 3. We pulled this out. We pulled this out. Okay. Awesome. I am going to reformat this one as well. Again, I would take in as much of the algebra as you can. It's really important to have your algebra down cold. Okay, there we are. All right, let's talk about the critical numbers now. All right, remember, so nope, there my brain went in the wrong direction. We're in the second derivative. Just second derivative is not critical numbers, that's first derivative. It's critical points for the second derivative. We're having a second derivative conversation. All right, so remember the critical points occur when y double prime equals to 0 or y double prime is undefined. So I need to look at both those cases. I need to also, and you guys may have noticed this at the beginning, I need to also think about if I have any domain restrictions, because domain restrictions cannot be critical points. So let's now go back up and think about that. You cannot let x equal to 0. So it's everything but 0. All right, so we've got to make sure we don't use an x value of 0 when we're down here. Okay, critical points. Okay, so this function will be equal to 0 when the numerator of the fraction is 0. So the numerator of the fraction will be equal to 0 when negative 2x plus 3 equals to 0, or 3 equals to 2x, or x equals to 3 over 2. All right, so our first critical point is 3 over 2. And when it's undefined. Now, this function cannot equal to 0. That's impossible. It's impossible to set e equal to 0. That's not solvable. But you can set this equal to 0, this x to the 4th. So notice okay, so I'm going to do it wrong and then I'm going to correct myself, okay, just so you can watch it happen in real time. So what I'm noticing is that x to the 4th equals to 0 when x is 0, right? I'm making that observation right now. That's what I'm talking about. I'm noticing that the function, okay, so I'm doing the case where it's undefined, where y double prime is undefined. That's when you would set the bottom equal to 0. Okay, my hand is not communicating with my brain. Hold on a second. Undefined. Y double prime is undefined when the denominator equals to 0. The denominator will equal to 0 when x to the 4th equals to 0, which means that would mean that x is equal to 0. But I do not want to put 0 here because it is already a domain restriction. So that is why it is not included down here, otherwise it would be. That is not to say, and make sure you've got this down, that is not to say that it isn't on the number line. Okay, that's not to say it isn't on the number line. It is, but it's on the number line as a domain restriction. It's on the you have to actually have it on here because it can change concavity around a domain restriction. So you have to have it on here. You just have to make sure you don't make any conclusions about what's happening here because there is no graph right here. There's no graph right here. All right, so now, and then let me put 3 over 2, which is a critical point. So this one's a domain restriction. This one's a critical point. So you can have some action happening over here, just not over there. When I say action, I mean inflection point. You can't have an inflection point where there's no graph. Okay, gang, you can see how much lovely room I left myself, so let me add some more space here so I can do this. Okay. Alright, so you guys know when we test for concavity, you got to plug into the second derivative. So let me write it down here. Alright, now I mentioned this in the lecture and I'm going to mention it again because it's really important. I just think for you guys, you know, when you're putting in so much work and time, if you can make the problem a little bit easier for yourself, you should take a moment to figure that out. Alright, so the first thing is you want to know if anything is ever positive, strictly positive or strictly negative. So for instance, the 3, this is a positive 3. So this little nugget right here, this little guy right here will always be positive. There's no variable there, so there's no plug-in. This x to the 4th will always be positive. So I'm not going to plug into that. I know that's positive. Now over here, this guy may confuse you for a moment, so let me talk you through this for 1 second. I'm going to simplify it for you to help with the concept. The e function, if you put a positive number into it, it's going to give you a positive answer. So like for instance, e squared is about 7.389. All right, now notice this. This is the part where students get confused. What if I put in e to the negative 2? When you put in a positive or a negative, it's still positive. When you put in a positive or negative, it's still positive. Okay, so e to the negative 2 is about 0.135. Now the reason why it's still positive is because a negative exponent doesn't make the e negative. What it does to the e is it flips it. So it doesn't do this. It doesn't actually make the e negative. It flips the e to the bottom. So the e will stay positive in either case. It's just whether the e is upstairs or downstairs. That's the only difference. So what I'm saying in a half an hour of winded words is that the e will always be positive. That is what I'm saying. Because whether you put in a positive or negative, it's positive. The negative only flips it to the bottom. The overall fraction will still be positive. Okay, woo! So the good news here is the only thing we actually have to plug into is this. This can be positive or negative. All right, here we go. I have to do something to the left of 0. So I'm going to go with negative 4. Now, everything is positive here except for this guy. So this is the only thing I'm really sort of thinking about. So negative 2 times negative 4 is positive 8. Positive 8 plus 3 is 11. So this will come out positive. So everything will be positive for this first piece. All right, great. So the second derivative is greater than 0. And we know if it's greater than 0, it's concave up. All right. Now let's pick something between 0 and 1.5. That would be 1. 1 would be a great value. Again, the only thing you have to plug into is this dude right here. So negative 2 times 1 is negative 2. Plus 3 is positive 1. So now this comes out positive. So everything is positive. So that means that this is positive. Okay, again, if it's greater than, the second root is greater than 0, it's concave up. All right. This is 3/2, so I'm going to put in something like positive 4 over here. If I put in positive 4, negative 2 times positive 4 is negative 8. Negative 8 plus 3 is negative 5. So this is negative. A negative times a positive divided by 2 positives is negative. All right, that means that this one is concave down. All right, so let's start with the first part of the answer, which is to talk about the concavity of the original function. So concave up from negative infinity to 0. Don't include 0 anywhere. Don't say from negative infinity to 3/2. Don't say that because you don't have the 0. You actually have to cut it. And then 0 to 3/2. Wow, it's 14 minutes. I'm going to have to put this in 2 parts. Holy cow. Okay, well, let me try. Concave down from 3/2 to infinity. All right, that is the concavity part. Now let's do inflection. Domain restrictions are never inflection points. Okay, so right away I don't have to deal with that. Now here, is this an inflection point? So how you decide is you look to the left and right of the critical point. To the left side it's concave up. To the right side it's concave down. the definition of an inflection point is that it flips concavity. And this has indeed flipped or changed concavity. So yes, this would be an inflection point. All right, so that's an inflection point. Now you have to find the actual point on the graph. Remember, we're moving towards graphing. All right, so we have an inflection point at 3/2 something. Remember, you do not put this into the second derivative. In the second derivative, this is actually equal to 0. That doesn't do anything for me. That would be the value of y double prime. I want the value of y. To get the value of y, you have to plug it into the original. The original is y equals to e to the negative 3 over x. I'm rushing a little bit because I am racing the clock here. Alright, so I'm plugging in the x value of 3 over 2. So let's just do the little bit of math there. Negative 3 divided by 3 over 2 is negative 3 times 2 over 3. Cross this out. This is negative 2. E to the negative 2. Holy cannoli. We did it, gang. We got this video in there. That is your inflection point. 16 minutes later. Alright, gang. I do hope this is helping you. I will catch you. Bye-bye.